Nature explodes with a vibrant palette of colors, painting our world in hues that captivate the senses and inspire awe. From the lush greens of rainforests to the fiery oranges of sunsets, we are surrounded by a visual feast that never ceases to amaze. But look closely and you'll notice something peculiar, something that stands out in its absence. One color remains surprisingly elusive in the animal kingdom: blue. It's a mystery that has puzzled scientists and nature enthusiasts alike. Red, yellow, green, these colors are commonplace in the animal world, adorning feathers, scales, and fur in a dazzling array of patterns and shades. Yet true blue, a color that evokes the vastness of the sky and the depths of the ocean, is a rare gem in the biological tapestry. Why is this so? What makes blue so special and scarce? Why is blue, a color so abundant in our physical world, so scarce in the living world? This question leads us to explore deeper into the realms of science. The answer lies in the fascinating interplay of chemistry, physics, and the evolutionary pathways that have shaped life on Earth. It's a story of how light interacts with matter and how life has evolved to use and reflect colors in unique ways. Butterflies, with their wings painted in 1,000 hues, provide a perfect starting point for our exploration of color in nature. These delicate creatures use color for a multitude of purposes, from camouflage to communication. The vibrant patterns on their wings serve as signals, attracting mates, warning predators, and even helping them blend seamlessly into their surroundings. Many of the colors we see in butterflies, and indeed in many other animals, are produced by pigments. These pigments, embedded within the butterfly's wings, act like tiny filters, absorbing certain wavelengths of light while reflecting others. The wavelengths that are reflected determine the color that we perceive. However, there's a crucial detail to remember. Blue pigment is exceedingly rare in the animal kingdom. Deep in the rainforests of Central and South America flutters a creature of breathtaking beauty, the morpho butterfly. Its wings, a dazzling spectacle of iridescent blue, shimmer and shift with every movement, captivating all who behold it. But the morpho's blue is not the product of pigment. Instead, it arises from a phenomenon known as structural color. Unlike pigments, which produce color by absorbing specific wavelengths of light, structural color arises from the interaction of light with microscopic structures on a surface. In the case of the morpho butterfly, the secret lies in the intricate architecture of its wings. The result is a vibrant, iridescent blue that seems to shift and shimmer with the changing angle of light. Section 4. Iridescence, nature's shimmering spectacle. The morpho's shimmering blue is a prime example of iridescence, a phenomenon where the color of a surface appears to change depending on the angle from which it is viewed. This dazzling display is not just a visual treat, but also serves various purposes in nature, such as camouflage and communication. This mesmerizing effect is not limited to butterflies. It can be observed in a wide range of natural and man-made objects, from soap bubbles to opals. Each of these objects showcases iridescence in its unique way, adding to the beauty and complexity of our world. Iridescence arises from the interplay of light with microscopic structures on a surface. These structures can be as intricate as the scales on a butterfly's wings, or as simple as the layers in a soap bubble. When light waves encounter these structures, they are reflected and refracted, creating interference patterns. These patterns are responsible for the shifting colors that captivate our eyes. These interference patterns can either amplify or cancel out certain wavelengths of light, depending on the angle of incidence. This dynamic interaction is what makes iridescent objects so fascinating to observe. The spacing of the microscopic structures, as well as the angle of incident light, determines the wavelengths that are amplified and thus the color that we perceive. This precise arrangement is a marvel of natural engineering. This is why iridescent objects often display a spectrum of colors that shift and change as the viewing angle changes. The result is a dynamic and ever-changing visual experience. In the case of the morpho butterfly, the intricate structures on its wings create a medium with a different refractive index than air. This difference in refractive index is what gives the morpho its stunning blue hue, a true wonder of nature. Section 5. Beyond the butterfly's structural color in the wild. The morpho butterfly is not alone in its mastery of structural color. Throughout the natural world, a dazzling array of creatures have evolved similar strategies to produce vibrant and iridescent hues. The brilliant blue feathers of the blue jay, for example, are not pigmented, but instead get their color from microscopic air pockets within the feather structure. These air pockets scatter incoming light, preferentially reflecting blue wavelengths back to the viewer. The iridescent plumage of peacocks, another striking example, is created by intricate arrays of melanin rods arranged in a crystal-like structure. From the shimmering scales of fish to the iridescent exoskeletons of beetles, structural color is a testament to nature's boundless creativity. Section 6. The Blue Abyss. A different story in the ocean. While blue is a rare treasure on land, it reigns supreme in the ocean depths. The vast majority of light entering the ocean is absorbed by water molecules, with blue wavelengths penetrating the furthest. This is why the ocean appears blue to our eyes. Many marine creatures have evolved to blend seamlessly into their blue surroundings. Some fish, for instance, have specialized cells called iridophores that contain stacks of reflective platelets. These platelets act like tiny mirrors, reflecting blue light back towards the surface and making the fish appear blue or silver to an observer. The ocean's depths also harbor creatures that produce their own bioluminescent light, often in shades of blue and green. Section 7. The Enigma of Blue, a late bloomer in evolution's palette. Despite its abundance in the physical world, blue remains a rare gem in the biological realm, particularly when it comes to pigments. The sky and the ocean are drenched in blue, yet this color is surprisingly scarce among living organisms. While plants have evolved various ways to create blue pigments, animals, for the most part, seem to have missed the memo. Blue flowers and butterflies are a testament to nature's ingenuity, but the animal kingdom tells a different story. The rarity of blue pigment in vertebrates in particular is striking. Even the vibrant blue of a peacock's feather or the skin of a blue frog is not due to pigment, but rather structural coloration. While some exceptions exist, such as the mandarin fish and the olive-winged butterfly, the vast majority of vertebrates lack the ability to produce blue pigment. These rare examples stand out precisely because they are so uncommon. This raises a question: why is blue pigment so elusive in the animal kingdom? Scientists have long pondered this mystery, seeking answers in the annals of evolutionary history. One prevailing theory suggests that the ability to create blue pigment evolved relatively late in evolutionary history. Early life forms may not have had the biochemical pathways necessary to produce blue pigments. Early animals may have relied primarily on camouflage for survival, favoring colors that blended well with their surroundings, such as browns, greens, and yellows. These colors provided a practical advantage in evading predators and hunting prey. Instead, many animals, like the morpho butterfly, developed ingenious ways to create blue through structural color, exploiting the laws of physics to achieve the desired visual effect. This method involves microscopic structures that reflect and refract light to produce the vivid blue hues we see. From reflective coatings for solar panels to vibrant pigments for paints and cosmetics, the study of structural color holds immense potential for technological innovation. By mimicking nature's methods, we can create sustainable and efficient solutions for a variety of applications.